Welcome back, Digital Electronics. Moving forward as always. Alright, we're going to be looking at the 7-segment display driver. Okay, so it's the 74LS47. We're going to be doing some breadboarding with this as well. Alright, so we have to make sure that we look, this is kind of an excerpt from a data sheet on here. But essentially what the 74LS47 7-segment display driver is doing is it's taking the binary code that we input to it. Alright, so we can input up to 4 bits. We can input A, B, C, and D into this specific controller, alright, or a driver, however you want to interpret it. Alright, and what it's going to do is based on the values of A, B, C, D, so 0, 0, 0, 0 up to 1, 1, 1, 1. Alright, so 0 to 15. We can input those 4 bits and it's going to translate it into the digits, right, for us 0 to 9, and then it's going to translate up to 15 for when it's going to be equivalent to, right, of A, B, C, D to 15. Okay, so if we take a look at them, look at the outputs on this chip. This chip is what? It's a little bit bigger than what we've been working with. It's 16 pins instead of the 14 pins. So very important that we pay attention to that piece. It's a 16 pin chip. So VCC is going to go to pin 16. So when we breadboard, we're going to breadboard 5 volts to pin 16. And we're going to pin 8 is going to go to ground. Okay? And then whatever we're driving it with is going to go into A, B, C, and D for our inputs. Okay, we're not going to worry about RBI and RBO and things like that right now. But if we look at the outputs, all right, A, B, C, D, E, F, and G, those are going to go to each specific segment on our 7-segment display. So you need to make sure that you go through resistors for this. So the 74LS47, what we do need to know is that it is working with a common anode. So all the outputs for this are going to be low, because remember, anode 0 turns it on, so anode is going to be pre-wired by you to 5 volts. Alright, so all of the outputs of this driver are going to be low. Now this is the input of the chip. I don't want you to necessarily focus on this. This is what's inside that chip, okay, the logic behind it. So notice that it's all based with NAND technology. Alright, so you can see all the NAND gates in there. There's a few AND gates and things like that, but for the most part, it's doing and driving everything through the NAND technology, how to input it. So this is all done. This is a much more advanced level class when we start looking at chip design and that sort of thing. But that's what's inside the chips and how it's controlling the outputs. Alright, so what's important for us is to understand the truth table here. Alright, and we can see what the output's going to be on the truth table and which segments are going to be on and which segments are going to be off. Alright, so if we look at the truth table here, our decimal input is 0. So if we look at A, B, C, and D, notice how it's L, 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 and L. Well, L, 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 and L means low for us. So for us in our truth table, we can interpret that as 0, 0, 0, 0. Okay, so when we look at the output, alright, to put on a 0, okay, if we're looking at each segment, remember, I want you to sort of think back about how we controlled the date of birth. It's the same kind of concept here. So if we look at segments A through G there, notice that it's L, 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 and H, right? G is getting the H. G is getting the high signal because we are turning G off. All the other segments, A, B, C, D, E, and F, need to be on to produce a 0, and G needs to be off, alright, for us to produce a 0. So that's really how it translates back and forth. So we've already kind of covered this and how to control the different segments when we did the date of birth project, so I'm not going to spend a ton of time on here, but you should be able to go through this truth table and understand L is equal to 0, H is equal to 1, and how we're controlling those segments. So if we look at the last one, or not the last one, but the next one, I'll look at the decimal equivalent of the number 1. Alright, so for us, that our input needs to be 0, 0, 0, 1, so that's why we have low, 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 high, because that's our binary equivalent of the decimal 1. And for the outputs, all right, segment A needs to be high because we don't want segment A and on. To produce the number 1, we just want segment B and C to be on. So if we look at the truth table here under the outputs, all right, the only thing that should be on and getting low is B and C. So notice B and C are both low. All the other segments are high because they should be a 1, and B and C should each be a 0. So A, D, E, F, and G are all a 1. B and C are each a 0. That's how we're producing a 1. So this is very fundamental, but we did a lot of this, guys, and this is exactly, like I said, how we controlled the 7-segment display doing date of birth. This is just a chip that does it for us, okay? So that's the beauty of it. So we can set it up, and you're going to do a lab in class where you do the 7-segment display driver, and you're going to set it up this way. All right, make sure that you choose common anode. Make sure that you put a resistor beforehand. So, same when we breadboard this up, you're going to want to have a resistor beforehand so that you don't blow the segments on the 7-segment display. So we can also use our breadboard companion to drive this with our switches, right? Since we have 4 switches on there, you're going to send your breadboard companion to A, B, C, and D. If we aren't using one of those, so say we were only using like A, B, and C, and we weren't using D, we would send D to ground, okay, so that it would be constantly low for us in that case. All right, so just know if we didn't need to use them all, we would only use the specific ones. The inputs not used always are going to be default and go to ground. All right, so RBI, RBO, all that, it's going to go to 5 volts, okay? And then we have our different drivers that are going out for segments A, B, C, and D. And all of that, I'm going to step back a couple slides, is going to be based on the connection diagram here. So we're going to breadboard through this in class just so that you get a good idea of how to drive the 7-segment display just with some switches, and then we'll automate it. Now, I did show you some videos for the modulus asynchronous counter that had this already in there. All right. It doesn't really matter to me which order you watch this in because I want you to watch them all in. But this is where that driver is when you watch the videos that I did in multi-sim using the flip-flops to do the modulus counters that we did. I believe we did a counter from 0 to 7. We did a counter from 1 to 4. And we did a counter from 3 to 6 that I did in the multi-sim videos. Where you can see where it's using this the 74 LS47. Okay. Using this driver, guys, it's much quicker and much easier, right? Then think of your date of birth. Essentially, you would have had to make like a date of birth thing that would do all that different logic that outputs each, specific digit that we want. And then not only that, but then you would have the other logic that we're going to feed into it with the flip-flop. So you'd have a really large schematic. So it's nice that we can have something that actually drives a 7-segment display for us as long as we feed it some inputs that it needs. Okay, so make sure you watch those multi-sim videos as well, and you're looking for the chip when you're putting this into multi-sim. It's the 74 LS47. But we're gonna, like I said, we're gonna breadboard this in class so that you can kind of see how this driver works, as well as with some of the projects that we're gonna go through as well. All right, guys, have a great day. I'll see you in class.